In this video, we're going to look at the pH of strong acids and strong alkalis. By the end of the lecture, you should be able to use the equation pH equals negative log of the concentration of the hydrogen ion to determine the pH of both strong acids and strong alkalis. You will find this equation in your data booklet. Right, the best way to learn how to work out the pH of strong acids and alkalis is just to try a few questions. So let's start with a nice easy one. What is the pH of a 0.1 mole per litre solution of hydrochloric acid? Well, hydrochloric acid, as you should know, is a strong acid. So it completely dissociates to give you hydrogen ions and chloride ions. So if I had a 0.1 mole per litre solution of HCl, I would have a 0.1 mole per litre concentration of H plus ions. So the H plus ion concentration is 0.1, which is equal to 10 to minus 1. So the pH of this solution would be 1. Okay, let's try a slightly harder example. What is the pH of a 0.2 mole per litre solution of hydrochloric acid? Okay, so we have our hydrochloric acid completely dissociating. So if we've got a 0.2 mole per litre solution of HCl, then we'll have a 0.2 mole per litre solution of H plus ions. Now, the difference here, of course, is that the concentration of the H plus ions is not an exact power of 10, as they all have been in all the examples you've looked at so far. Now 0.2 lies in between 0.1, it's greater than 0.1, but it's not as big as 1. So it lies in between 10 to the minus 1 and 10 to the 0. So the pH of this solution is going to lie in between 1 and 0. Where exactly in between 1 and 0 we can't tell. So let me introduce you to a new equation. pH equals negative log of the hydrogen ion concentration. This is what we'll use now to work out the pH of solutions. So in this case, the pH will be the negative log of the H plus ion concentration, which is 0.2. So it's really just a matter of getting used to your calculator. So the log of 0.2 is negative 0.7. So the pH is negative 0.7. So the pH of this solution would be 0.7. Okay. So now we can work out the pH even if the hydrogen ion concentration is not an exact power of 10. Okay, let's try this one. What is the pH of a 0.3 mole per litre solution of sulphuric acid? Now sulphuric acid, like hydrochloric acid, is a strong acid. If we have a 0.3 mole per litre solution of sulphuric acid, however, the concentration of H plus ions will be 0.6. It will be double the concentration of H2SO4, because every time a sulphuric acid molecule dissociates, it produces 2 H plus ions. So we've got a hydrogen ion concentration of 0.6. So using the equation of pH equals negative log H plus, and you will find this equation in your data booklet in the sheet at the front with all the formula in it. So the pH is the negative log of 0.6, okay, which comes out at negative 0.22. So the pH is 0.22. Okay, so the lesson from this question is to don't always assume that the concentration of the hydrogen ions is going to be the same as the concentration of the acid. It all depends if it's monoprotic like HCl, which which means it produces 1 proton, or diprotic, like sulphuric acid, which means it produces 2 protons. Okay, so far all our questions have been about acids. Let's try a couple with alkalis. So what is the pH of a 0.2 mole per litre solution of sodium hydroxide? Well, at the moment we're just working with strong acids and alkalis. Sodium hydroxide fully dissociates to give sodium ions and hydroxide ions. If we've got 0.2 mole per litre of sodium hydroxide, we'll have 0.2 moles per litre of hydroxide ions. Now, of course, in order to work out the pH, we need to know the concentration of H plus ions. So to convert our hydroxide ion concentration to a hydrogen ion concentration, we need to use the ionic product. Remember, the ionic product holds true for all aqueous solutions. And if, like this question, it doesn't specify that it's at room temperature, you just assume it is, and so the ionic product is 10 to the minus 14. So we know that 10 to the minus 14 is the product of the hydrogen ion concentration multiplied by the hydroxide ion concentration. So if we rearrange that, the hydrogen ion concentration is 10 to the minus 14 divided by the hydroxide ion concentration. So in this case it's 10 to the minus 14 divided by 0.2, which is 5 times 10 to the minus 14 moles per litre. So that's our hydrogen ion concentration. So we then stick that into our equation. pH equals negative log H plus. So negative log of 5 times 10 to the minus 14, and that gives an answer of 13.3. Alkaline, as you expect from a solution of sodium hydroxide. Okay, let's try one more. What is the pH of a 0.2 mole per litre solution of magnesium hydroxide? Difference in this case is that when the magnesium hydroxide dissociates, it produces 2 moles of hydroxide ions. So if our magnesium hydroxide concentration is 0.2, our hydroxide concentration will be 0.4. Okay, again, we need to work out our H plus ion concentration using the ionic product. So the hydrogen ion concentration is 10 to the minus 14 divided by 0.4, and that comes to 2.5 times 10 to the minus 14 moles per litre. So that's our hydrogen ion concentration. Stick that into our equation. pH equals negative log H plus. So negative log of 2.5 times 10 to the minus 14, and that comes to 13.6. Okay, so that's basically all there is to working out the pH of strong acids and strong alkalis. You just need to make sure what the concentration of the hydrogen ions concentration is, and then stick it into this formula which is in your data booklet. Okay, so now I suggest you pause the tape and try and work out the answers to these questions, which are similar to the ones that we've just gone through. Okay, so go and try and do that now. Okay, so the answers that hopefully you got for a 0.5 mole per litre solution of nitric acid, which is monoprotic, you should have got a pH of 0.30. For a 0.5 mole per litre solution of sulphuric acid, which is diprotic, you've got a pH of exactly 0. For the phosphoric acid, which is triprotic, so it produces 3 H plus ions, you should got an answer of negative 0.18. And for the 0.5 mole per litre solution of sodium hydroxide, you should have got an answer of 13.7. Right, there's probably just one other type of question that you could get asked. So in this question, you're told the pH, you're told your solution has got a pH of 3.6, and it asks you to work out both the hydrogen and hydroxide ion concentration. So we're going to use our relationship pH equals negative log H plus. So 3.6 equals negative log H plus. Okay, so swap them over and say the log of H plus equals negative 3.6. So in order to get the hydrogen ion concentration, you have to take the anti-log of 3.6, and you need to learn using your calculator how you can work out anti-logs. Usually it's sort of inverse log function. So the hydrogen ion concentration is the anti-log of negative 3.6, which comes out at 2.51 times 10 to minus 4 moles per litre. Okay, that's only half the question though. We also had to work out the hydroxide ion concentration, and for that we're going to use the ionic product. So the hydroxide ion concentration is going to be 10 to minus 14 divided by the hydrogen ion concentration. So 10 to minus 14 divided by this number here, 2.51 times 10 to minus 4, and that comes out at 3.98 times 10 to minus 11 moles per litre. So that's our hydrogen ion concentration, and that's our hydroxide ion concentration. So why don't you try this question now? Calculate the concentration of hydrogen ions and hydroxide ions in a solution with a pH of 9.3. So stop the lecture, try it, and then I'll give you the answers. Okay, so the answers you should have got was, for the hydrogen ion concentration, you should have got a value of 5.01 times 10 to the minus 10 moles per litre. And for the hydroxide ion concentration, you should got a value of 2.00 times 10 to the minus 5 moles per litre. So by now you should be able to use the equation pH equals negative log H plus to determine the pH of a variety of strong acids and strong alkalis.